Okay, in this next section, we're gonna cover two sections. 23.3 is Gauss's law, and 23.4 is the application of Gauss's law. It's a single slide. I don't feel like making a whole new uh, lecture just for that one slide. So let's share the PowerPoint. We place a charge inside a spherical Gaussian surface. When the charge is at the center of the sphere, the electric field is everywhere normal to the surface and constant in magnitude. So if it's normal to the surface, if the electric field is normal to the surface, you have E dot A is E A cosine theta, cosine theta being, since it's zero, cosine of zero is equal to 1, so E A cosine theta is just equal to EA for this particular case. So if we take E equals KEQ divided by R squared, that's just Coulomb's law, where KE is equal to 8.99 times 10 to the ninth Newton meter squared per Coulomb squared. Now, if we again, as I was saying, if we look at E dot delta AI, where both of those are vectors, E dot delta A is just E delta AI, because the E delta AI times cosine theta, in every case, the cosine theta here is equal to 0, and so you just end up, cosine of 0 is equal to 1, so you just end up with E delta AI. So the flux is equal to the integral of all those E dot DAs, and that's because of the cosine of 0 being 1. That's just the integral of E dA, and we pull out the E, and it's just the integral of, it's E times the integral of dA, and the dA, the integral of dA is the surface of a sphere. So the electric flux is KEQ R squared, that's the E part, times 4 pi R squared. 4 pi R squared is the surface of a sphere. Now, if you so the R's cancel, and you end up with 4 pi KE squared. Now, early on in the last chapter, when we talked about KE, we also defined KE as 1 over 4 pi epsilon 0, where epsilon is the permittivity of free space, and permittivity of free space is 8.8542 times 10 to the minus 12 Coulomb squared over Newton meter squared. So if KE is equal to 1 over 4 pi epsilon 0, you substitute that in, the 4 pi's cancel, and all you're left with is the electric flux is K divided by epsilon 0. And what's that saying? That's saying that the flux is equal to the charge divided by epsilon 0. Whatever the charge inside is equal to epsilon 0, that's the electric flux coming out of the sphere. It's the Q inside the sphere times epsilon 0. Well, now we're talking about a sphere here, but really the net electric flux is the same through all surfaces. So whether we define it as a sphere at S1 or a blob at S2 or a bigger blob at S3, it's the same. The electric flux is the same in all cases. So the net flux through any closed surface surrounding a point charge Q is given by Q divided by epsilon 0, and is independent of the shape of that surface. Is key point there. Now, if the charge is outside the surface, the number of field lines entering the surface equals the number leaving the surface. So you remember we said that when it goes in, it's negative. When it comes out, it's positive. If it's going in, it's negative. If it's coming out, it's positive. So they cancel. So if a charge is outside a sphere, the total the total number of field lines is 0. So let's look at some situations here. Charge Q4 does not contribute to the flux through any surface because it is outside all of the surfaces. So Q4, it doesn't contribute to the flux. Now it will contribute to the electric field that's present, but not to the flux. So every field line that's coming out of Q4, if it enters S, it'll exit S. If it enters S prime, it'll exit S prime. If it enters S double prime, it'll exit S prime. So it doesn't contribute any flux through the surface because they all cancel. So here the integral of E dot dA is the integral of all of these E's, E1 plus E2 plus whatever times dA. So the electric flux is the integral of E dot dA, and that simplifies to the Q inside. It's the Q inside divided by epsilon 0. So if we look at S, that's Q1. It's negative. It's Q1 divided by epsilon 0. If we look at S prime, it's Q2 plus Q3. I understand that Q3 is negative, but it is Q2 plus Q3 divided by epsilon 0. And S, well, there's no charge inside, so it's the electric flux in it is 0. Now, if the net flux through a Gaussian surface is 0, the following 4 statements could be true. Which of the statements must be true? There are no charges inside the surface. Well, now, it could be that you have a plus and a minus that kind of cancel each other out. So A doesn't necessarily mean that there's no charges. The fact that you have the net flux through the Gaussian surface being 0 means that you could have a positive and you could have a negative, and they would cancel each other. The net charge inside the surface is 0. Well, that would happen even if you had a plus and a minus. The net charge would be 0. That's it, assuming that they're of equal value. A plus, let's say like a plus 1 microcoulomb and a minus 1 microcoulomb. Then the net charge would be 0, and there would be no net flux through them. So the net charge inside the surface has to be 0. The electric field is 0 everywhere on the surface. That doesn't necessarily have to be true, but the number of electric field lines entering the surface equals the number leaving the surface. That has to be true. So it's, in this case, it's B and A. I'm sorry, B and D. B and D. Okay? Now, application of law, this is actually section 23.4. The electric flux is equal to E dot dA is equal to Q inside divided by epsilon 0. What does that mean? Well, it means that E is constant over the portion of the surface. The electric field is constant over the portion of the surface. If E and dA are parallel, if they're parallel, that means that the theta is equal to 0, and E dot dA is equal to EDA cosine theta. Cosine of 0 is 1, so it's just E dot dA. If they're perpendicular, the cosine of 90 degrees is equal to 0, so E dot dA is EDA cosine of 90 degrees, which is 0. And if E is equal to 0, E is equal to 0 over a portion of the surface. Those are the applications of the of the application of Gauss law to uh, various charge distributions. In the they follow it with a bunch of examples. I'm not going to go through the examples. I am going to do some homework problems that show what I'm expecting you to do. And with that, we'll stop this section.